In the vast quiet of space, far from planets and familiar skies, stars begin their lives in regions that are almost invisible. These regions are known as molecular clouds. They are enormous, cold accumulations of gas and dust, mostly composed of hydrogen. At first glance, they may appear still and uneventful, drifting slowly through the galaxy. But within them, subtle processes are constantly unfolding. Gravity plays the central role. Even a slight increase in density within a cloud can begin to attract more material. Over time, this attraction causes gas to gather into denser regions, forming what are known as protostellar cores. This process is extremely slow. It can take millions of years for a region within a cloud to collapse enough to form a protostar. But once the collapse begins, it tends to continue. As the gas falls inward, it accelerates and heats up. The center of the forming star becomes hotter and denser, while the surrounding material often forms a rotating disk. These disks are not just byproducts of star formation. They are also the places where planets can eventually form. In this sense, the birth of a star and the formation of a planetary system are closely connected processes. At the center of the collapsing cloud, temperature and pressure continue to rise. Eventually, they reach a point where nuclear fusion becomes possible. Hydrogen nuclei begin to fuse into helium, releasing enormous amounts of energy. This moment marks the true birth of a star. From that point forward, the star enters a stable phase known as the main sequence. The balance between gravity pulling inward and energy pushing outward keeps the star in equilibrium. Without this balance, the star would either collapse or expand uncontrollably. Observations of star-forming regions have been greatly improved by modern telescopes. Instruments launched with the help of organizations like NASA allow scientists to study these distant clouds in remarkable detail. Images captured by the James Webb Space Telescope reveal structures within these clouds that were previously hidden. We can now see the early stages of star formation, the swirling disks of gas, and the jets of material being ejected from young stars. These observations confirm that star formation is not a rare event. It is happening constantly throughout galaxies, even now. In fact, many of the stars visible in the night sky began their lives in clouds similar to those we observe today. The process may seem calm and distant, but it is also deeply connected to everything around us. The sun itself formed in a molecular cloud billions of years ago. The Earth and everything on it is a result of that process. And even now, new stars continue to form, carrying the story of the universe forward. Once a star is born, its life is determined primarily by one factor: its mass. Mass defines how hot the star will burn, how long it will live, and how it will eventually die. Smaller stars, like red dwarfs, burn their fuel very slowly. They can exist for tens or even hundreds of billions of years. Larger stars, on the other hand, burn through their fuel much more quickly. They shine brightly, but their lives are relatively short. During the main sequence phase, a star remains stable. Hydrogen fusion in its core produces energy that balances the inward pull of gravity. This phase can last for millions, billions, or even trillions of years, depending on the star's mass. Over time, however, the hydrogen in the core begins to run out. As this happens, the balance that maintained the star begins to change. The core contracts under gravity while the outer layers expand. The star becomes a red giant. In this phase, the star grows much larger than it was before. Its outer layers cool, giving it a reddish appearance. Inside the core, new types of fusion may begin, producing heavier elements. The exact path a star takes from this point depends again on its mass. Some stars will shed their outer layers gently, forming beautiful structures known as planetary nebulae. Others will undergo far more dramatic transformations. Understanding these life cycles is one of the key goals of modern astronomy. Observations from NASA and missions supported by private companies like SpaceX provide data that help scientists refine their models. By studying stars at different stages of their lives, researchers can piece together the full story of stellar evolution. This story is not only about stars, it is also about the elements that make up planets, atmospheres, and life. Every stage of a star's life contributes to the chemical evolution of the universe. In a sense, stars are not just objects in space. They are engines of transformation. As a star continues its long and steady life, there comes a moment when the balance that once defined it begins to shift. For millions or billions of years, the star has quietly fused hydrogen into helium in its core. This process produces the energy that keeps the star stable, holding gravity in balance. But over time, the supply of hydrogen in the core begins to run out. This does not happen suddenly. It is a gradual change, almost unnoticeable at first. Yet the consequences are profound. When the hydrogen in the core is depleted, fusion slows down in that central region. Without the outward pressure generated by fusion, gravity begins to take over. The core starts to contract. As it contracts, it heats up. At the same time, hydrogen fusion continues in a shell around the core, where hydrogen is still present. This shell burning produces additional energy, and that energy causes the outer layers of the star to expand. The star grows larger, much larger. It becomes what astronomers call a red giant. In this phase, the star can expand to many times its original size. If a star like our Sun were to enter this stage, it could grow large enough to engulf the inner planets. Despite this dramatic expansion, the outer layers of the star actually become cooler. This gives the star a reddish appearance, which is why it is called a red giant. Inside the core, conditions continue to change. As temperatures rise, new types of fusion can begin. Helium can fuse into carbon, and in more massive stars, even heavier elements can be produced. This stage of stellar evolution is complex and varies depending on the mass of the star. Smaller stars may not reach the temperatures needed to fuse heavier elements. Larger stars, however, can go through multiple stages of fusion, creating a layered structure within the core. Each layer represents a different stage of fusion, with heavier elements forming deeper inside. Observations from missions supported by NASA allow scientists to study red giants in detail. By analyzing their light, researchers can determine their composition, temperature, and size. These observations reveal that red giants are not rare. They are a natural and expected phase in the life of many stars. The transformation into a red giant is not violent in the way a supernova is, but it is still a dramatic change. A star that once appeared stable and unchanging becomes something much larger, cooler on the surface, yet more active within. It is a reminder that even the most stable systems can evolve over time. For some stars, the story does not end quietly. Instead, it ends in one of the most powerful events in the universe, a supernova. Supernovae are not all the same. There are different types, each with its own cause, but they all share one defining feature: an enormous release of energy. In the case of massive stars, the process begins after the star has fused elements all the way up to iron in its core. Iron is different from lighter elements. Fusing iron does not release energy. Instead, it consumes energy. This creates a problem. The star can no longer produce the outward pressure needed to balance gravity. The core collapses. This collapse happens incredibly fast, in a matter of seconds. The outer layers of the star fall inward, crashing into the core. The result is a powerful shock wave that travels outward, tearing the star apart. This is a core collapse supernova. The explosion is so bright that it can outshine an entire galaxy for a short period of time. In that brief moment, more energy is released than the star produced during its entire lifetime. Supernovae play a crucial role in the universe. They are responsible for creating many of the heavy elements that cannot be formed through normal stellar fusion. Elements like gold, uranium, and many others are forged in these extreme conditions. When a supernova occurs, these elements are scattered into space. They become part of the interstellar medium, the material from which new stars and planets will form. In this way, supernovae contribute directly to the chemical evolution of the universe. There is also another type of supernova, known as a Type 1a supernova. This occurs in binary star systems, where one star is a white dwarf. If the white dwarf pulls too much material from its companion, it can reach a critical mass. At that point, a runaway fusion reaction begins, leading to a powerful explosion. Type 1a supernovas are particularly important for science. Because they have a consistent brightness, they can be used as standard candles to measure distances in the universe. Observations of these supernovae have led to the discovery that the expansion of the universe is accelerating. Research conducted with support from NASA and observations made possible by launches from companies like SpaceX, continue to improve our understanding of these events. Despite their violence, supernovae are part of a larger cycle. They mark the end of one star's life, but also the beginning of new possibilities. The material they release becomes the foundation for future stars, planets, and perhaps even life. In that sense, even destruction becomes a form of creation. When a massive star reaches the end of its life and explodes as a supernova, not all of its material is thrown into space. What remains at the center can become one of the most extreme objects in the universe, a neutron star. After the core of the star collapses, gravity compresses the remaining matter to an extraordinary degree. Protons and electrons are forced together, combining to form neutrons. What is left is an object composed almost entirely of these tightly packed particles. The result is something incredibly dense. A neutron star can have a mass greater than that of the Sun, yet be only about 20 kilometers in diameter. This means that a single teaspoon of neutron star material would weigh billions of tons. The surface of a neutron star is unlike anything we experience on Earth. Gravity there is immensely strong. If you could stand on it, which is not possible, your weight would increase by billions of times. Even light struggles to escape its pull, though not as completely as in a black hole. Neutron stars also rotate very rapidly. When the original star collapses, it conserves angular momentum. As its size decreases, its rotation speeds up, much like a spinning figure skater pulling in their arms. Some neutron stars can rotate many times per second. They also possess extremely strong magnetic fields. These magnetic fields can channel particles into beams that extend out into space. Observations of neutron stars have been made using data from missions supported by NASA, providing insights into their structure and behavior. Even though they are small compared to stars, neutron stars are powerful and dynamic objects. They represent a state of matter that cannot be replicated under normal conditions. And they show just how extreme the universe can become. Some neutron stars are observed in a very special way. They are known as pulsars. A pulsar is a rapidly rotating neutron star that emits beams of radiation from its magnetic poles. These beams sweep across space as the star rotates. If one of these beams points toward Earth, we observe it as a regular pulse of radiation. This pulsing signal can be incredibly precise. In some cases, pulsars rotate with such stability that their pulses can be measured with extreme accuracy, almost like cosmic clocks. The discovery of pulsars was unexpected. At first, their regular signals were so unusual that scientists briefly considered the possibility that they might be artificial. However, further study revealed their true nature. Pulsars provide valuable information about the physics of neutron stars. By studying their rotation and emission, scientists can learn about the internal structure of these objects, their magnetic fields, and how they evolve over time. Some pulsars are part of binary systems, orbiting other stars or even other neutron stars. In such systems, complex interactions can occur. Matter can be transferred from one object to another, altering the behavior of the pulsar and sometimes producing intense bursts of radiation. Observations supported by NASA and data collected through advanced instruments, launched with the help of companies like SpaceX, continue to expand our understanding of pulsars. These objects are not only fascinating in their own right, they are also useful tools. Because of their regular pulses, they can be used to study gravitational waves, test theories of relativity, and even help map the structure of our galaxy. In the quiet darkness of space, pulsars act like distant beacons, marking time with steady, repeating signals. While individual stars can be studied on their own, many stars are born and exist within larger groups known as star clusters. These clusters are collections of stars that formed from the same molecular cloud and are bound together by gravity. There are two main types of star clusters: open clusters and globular clusters. Open clusters are relatively young and loosely bound. They often contain a few hundred to a few thousand stars. These stars are usually found in the disks of galaxies, including our own Milky Way. Because they formed together, the stars in an open cluster have similar ages and chemical compositions. This makes them useful for studying stellar evolution. Globular clusters, on the other hand, are much older and more densely packed. They can contain hundreds of thousands or even millions of stars. These clusters are typically found in the outer regions of galaxies, forming a kind of halo around them. Globular clusters are among the oldest structures in the universe. Studying them provides insight into the early history of galaxies and the conditions that existed when they formed. Within a cluster, stars can interact with each other in ways that isolated stars cannot. Close encounters can alter orbits, and in some cases, stars can even collide or merge. These interactions add complexity to the study of stellar evolution. Observations from telescopes, supported by NASA, allow scientists to analyze star clusters in detail, measuring their composition, motion, and age. Clusters also serve as natural laboratories. By studying stars within the same cluster, researchers can isolate variables and better understand how stars evolve over time. Private space companies, like SpaceX, contribute indirectly by enabling the launch of instruments that expand our ability to observe these systems. Star clusters remind us that stars are not always solitary. They are often part of larger systems, shaped not only by their own properties, but also by their interactions with others. And within these clusters, the story of stellar life continues, repeated across countless stars, each following its own path. Not all stars end their lives in the same way. For the most massive stars, the final stage of evolution can lead to something even more extreme than a neutron star, a black hole. After a massive star explodes as a supernova, its core may continue collapsing under its own gravity. If the remaining mass is large enough, nothing can stop this collapse. There is no known force that can resist it. The core compresses further and further, becoming smaller and denser until it reaches a point where gravity becomes overwhelming. At this stage, the escape velocity exceeds the speed of light. This means that nothing, not even light, can escape. The boundary around this region is called the event horizon. Once something crosses this boundary, it cannot return. From the outside, a black hole appears dark and silent. It does not emit light in the usual sense. However, its presence can still be detected. Matter falling toward a black hole can form an accretion disk, heating up and emitting intense radiation before crossing the event horizon. Black holes can also influence the motion of nearby stars, bending light and distorting space around them. Observations supported by NASA and data from space telescopes have provided strong evidence for the existence of black holes, both in stellar systems and at the centers of galaxies. Some black holes are relatively small, formed from individual stars. Others are supermassive, containing millions or even billions of times the mass of the Sun. These supermassive black holes are found at the centers of most galaxies, including our own. Despite their name, black holes are not simply empty voids. They are regions where space and time behave in ways that challenge our current understanding of physics. Research into black holes continues to push the boundaries of science, and even now, they remain one of the most fascinating and mysterious objects in the universe. The life of a star is not a single path. It is a range of possible journeys, each determined by mass, composition, and environment. Some stars end quietly. Smaller stars, after becoming red giants, shed their outer layers gently. These layers drift away into space, forming glowing clouds known as planetary nebulae. At the center, the remaining core becomes a white dwarf. White dwarfs are dense, stable remnants that no longer undergo fusion. They slowly cool over time, fading gradually into darkness. This process can take billions or even trillions of years. Larger stars follow more dramatic paths. They may explode as supernovas, leaving behind neutron stars or black holes. In these cases, the end of a star's life is not quiet. It is a powerful event that reshapes its surroundings. The material ejected during these explosions becomes part of the interstellar medium. This material is not wasted. It is recycled. New stars form from it. New planets take shape. In this way, the death of one star contributes to the birth of others. Observations from missions supported by NASA continue to track these processes across the galaxy. Each stage of stellar death provides information about the physics of extreme environments. It also reveals how elements are distributed throughout space. Without the death of stars, the universe would remain simple. There would be no heavy elements, no complex chemistry, no planets, and no life. Stellar death is not just an ending, It is part of a continuous cycle, a cycle that connects generations of stars across vast stretches of time. After a star has completed its life cycle, something always remains. It may be a white dwarf, slowly cooling in the darkness. It may be a neutron star, spinning rapidly and emitting pulses of radiation. It may be a black hole, silent and invisible, shaping space through gravity. Or it may be a cloud of gas and dust, drifting through space, carrying the elements that will one day form new stars. In every case, the remnants of a star become part of the future. The universe is not static. It is constantly changing, constantly evolving. Stars are born, live their lives, and eventually die, but their influence does not end. The elements created in stars become part of new systems. Carbon becomes part of organic molecules. Oxygen becomes part of atmospheres. Iron becomes part of planetary cores. Even the atoms that make up the human body were once inside stars. This connection between stars and life is one of the most profound ideas in science. It shows that the universe is not just a collection of distant objects. It is a connected system where processes that occur billions of years ago continue to shape the present. Organizations like NASA, along with growing contributions from private companies such as SpaceX and Blue Origin, continue to explore these processes. Each new mission adds to our understanding. Each new observation reveals more detail, and yet there is always more to learn. The life and death of stars is not just a scientific topic, it is a story, a slow, continuous process that unfolds across time and space. And as we observe it, we are also part of it, because in a very real sense, we are made of what remains.